Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Across the landscape of 20th century theoretical physics strode George Sudarshan, a figure whose profound insights reshaped our understanding of light and matter. His journey began in India, nurtured by the early influence of Homi Bhabha, the architect of India's nuclear program. Bhabha ignited in Sudarshan a deep fascination with the fundamental laws governing the universe, steering him toward a path of rigorous theoretical inquiry. This path led him to the University of Rochester, where he pursued doctoral studies under the guidance of Robert Marshak, a prominent particle physicist. Marshak's mentorship proved pivotal in shaping Sudarshan's research trajectory. The intellectual atmosphere at Rochester, charged with the excitement of burgeoning discoveries in quantum field theory, provided fertile ground for Sudarshan's intellectual development. It was during this period that Sudarshan began grappling with a fundamental challenge in quantum optics: the adequate description of the coherence properties of light. Prior to Sudarshan's groundbreaking work, the understanding of light's coherence was largely confined to classical descriptions. While classical electromagnetism provided a powerful framework for analyzing many optical phenomena, it fell short when dealing with the subtle quantum effects that arise in situations involving weak light sources or highly correlated photons. The very nature of coherent light itself, exhibiting wave-like interference patterns even at the single photon level, demanded a quantum mechanical treatment. Existing quantum mechanical descriptions, however, struggled to fully capture the range of possible states of the electromagnetic field, while the concept of coherent states, introduced by Erwin Schrödinger and later developed by Roy J. Glauber, offered a valuable tool for describing laser light and other highly ordered forms of radiation. These states represented only a limited subset of all possible quantum states. A comprehensive framework was needed, one capable of encompassing both classical light coherent states and more exotic, non-classical states exhibiting purely quantum mechanical behavior. This framework would need to address the description of partially coherent light, a common occurrence in nature, where the electromagnetic field exhibits some degree of order but lacks the perfect coherence of an ideal laser beam. Sudarshan provided such a framework with his introduction of the diagonal representation, now widely known as the Sudarshan-Glauber representation, or the P-representation. This representation, detailed in a seminal 1963 paper published in Physical Review Letters *, offered a revolutionary way to describe any quantum state of the electromagnetic field as a weighted superposition of coherent states. In essence, Sudarshan demonstrated that any density operator describing the quantum state of light could be expressed as an integral over coherent states, with a weighting function, p, that characterizes the statistical distribution of these states. The P-representation provided a complete and general description of the electromagnetic field, encompassing all possible quantum states, including those exhibiting non-classical properties, such as squeezing and anti-bunching. These non-classical states, which possess no direct classical analog, are crucial for applications in quantum information processing and high-precision measurements. A key advantage of the P-representation lay in its ability to handle partially coherent light. By introducing the weighting function, p, Sudarshan provided a mathematical tool to quantify the degree of coherence present in a given light source. A broad p-function indicates a high degree of incoherence, while a sharply peaked p-function corresponds to a highly coherent state. This allowed physicists to move beyond idealized descriptions of perfect coherence and to analyze the behavior of real-world light sources with varying degrees of order. The initial reception to Sudarshan's P-representation was met with skepticism from some quarters. Some physicists questioned the mathematical rigor of the representation, particularly in cases where the p-function became highly singular or ill-defined. However, Sudarshan rigorously defended his approach, demonstrating its mathematical consistency and physical validity. Over time, the P-representation gained widespread acceptance as its power and utility became increasingly apparent. Its ability to provide a unified description of all quantum states of light, including non-classical states and partially coherent light, made it an indispensable tool for researchers in quantum optics. The impact of Sudarshan's work on quantum optics extends far beyond its initial theoretical formulation. The P-representation has become a cornerstone of modern quantum optics, finding applications in a wide range of areas, from the study of laser dynamics to the development of quantum communication protocols. It continues to be taught in advanced quantum mechanics courses around the world, serving as a testament to its enduring significance. The P-representation also plays a crucial role in quantum information theory, where non-classical states of light are exploited for tasks such as quantum key distribution and quantum computation. The ability to characterize and manipulate these states, facilitated by the P-representation, is essential for realizing the full potential of quantum technologies. In essence, the P-representation provides a mathematical language for describing and understanding the quantum nature of light, enabling scientists to harness its unique properties for a variety of applications. Roy J. Glauber, whose work on coherent states provided a foundation for Sudarshan's P-representation, further popularized these concepts. Glauber's work, while distinct from Sudarshan's, built upon the framework established by Sudarshan, contributing significantly to the development of quantum optics as a whole. The contributions of both Sudarshan and Glauber have fundamentally reshaped our understanding of light and its interaction with matter. Sudarshan's early work on quantum optics, spurred by Bhabha's initial inspiration and nurtured by Marshak's guidance, laid the groundwork for his subsequent groundbreaking contributions to theoretical physics. The Sudarshan-Glauber representation stands as a testament to his profound insight and mathematical prowess, a lasting legacy that continues to shape the field of quantum optics today. His contributions extend far beyond this representation, encompassing fundamental insights into the nature of weak interactions, a journey that began with a bold proposal to unravel the mysteries of parity violation. Sudarshan's early work on quantum optics, spurred by Bhabha's initial inspiration and nurtured by Marshak's guidance, laid the groundwork for his subsequent groundbreaking contributions to theoretical physics. The Sudarshan-Glauber representation stands as a testament to his profound insight and mathematical prowess, a lasting legacy that continues to shape the field of quantum optics today. His contributions extend far beyond this representation, encompassing fundamental insights into the nature of weak interactions, a journey that began with a bold proposal to unravel the mysteries of parity violation. The mid-20th century presented a formidable challenge to physicists understanding the fundamental forces governing the subatomic world. Among these, the weak interaction responsible for phenomena like beta decay stood shrouded in mystery. Prior to the Standard Model's emergence, physicists grappled with diverse experimental observations that defied a unified explanation. One particularly perplexing puzzle involved parity violation. Parity, in simple terms, refers to the symmetry of a physical system under spatial inversion, a mere reflection. The strong and electromagnetic forces were believed to respect parity. However, experiments in the 1950s, particularly those involving the decay of cobalt-60, revealed that the weak interaction dramatically violated this symmetry. This meant that the mirror image of a weak interaction process did occur in nature with the same probability as the original process, a revolutionary and unsettling discovery. This experimental revelation presented a significant crisis for theoretical physicists. Existing theoretical frameworks struggled to accommodate parity violation, leading to a proliferation of competing models, each with its own set of assumptions and limitations. A comprehensive theory capable of explaining all observed phenomena related to weak interactions remained elusive. It was within this intellectual landscape that Sudarshan, in collaboration with his mentor Robert Marshak, embarked on a quest to formulate a new theory of weak interactions. Their collaboration culminated in the formulation of the VF theory, short for vector minus axial vector theory. This theory, published in their seminal 1958 paper titled Theory of Weak Interactions, proposed a universal description of weak interactions based on the chiral structure of the interacting particles. The central idea of the VF theory lies in the specific combination of vector and axial vector currents that mediate the weak force. These currents are mathematical constructs that describe the flow of particles and their intrinsic angular momentum, or spin, during a weak interaction. Before delving into the specifics, it's useful to understand the context. Previous attempts to describe weak interactions involved various combinations of scalar, pseudoscalar, vector, axial vector, and tensor currents. These models, however, suffered from inconsistencies and failed to provide a unified picture. The genius of the VF theory lies in its elegant simplicity and predictive power to positive that only a specific combination of vector and axial vector currents with equal magnitude but opposite sign contributes to the weak interaction. This particular combination is crucial because it directly incorporates the observed parity violation. The axial vector current changes sign under parity transformation, while the vector current remains unchanged. The VF combination therefore ensures that the weak interaction, as described by the theory, violates parity maximally, aligning perfectly with experimental observations. Specifically, the VF theory proposed that the weak interaction current is proportional to gamma mu, representing the vector part, minus gamma mu times gamma 5, representing the axial vector part, where gamma mu are the Dirac gamma matrices and gamma 5 is the chirality operator. This mathematical formulation has profound implications. It dictates that only left-handed particles and right-handed antiparticles participate in weak interactions. Chirality, a property related to the spin of a particle relative to its direction of motion, plays a central role in the VF theory. Left-handed particles have their spin oriented opposite to their direction of motion, while right-handed particles have their spin aligned with their direction of motion. The VF theory elegantly explains why neutrinos are observed to be only left-handed and antineutrinos only right-handed. The VF theory offered a resolution to numerous discrepancies plaguing earlier models. It provided a consistent framework for understanding both beta decay, the radioactive decay process, where a neutron transforms into a proton, electron, and antineutrino, and muon decay, where a muon decays into an electron, antineutrino, and muon neutrino. The theory accurately predicted the energy spectra and angular correlations of the emitted particles in these decays, providing strong support for its validity. Furthermore, the VF theory naturally incorporated the concept of a universal Fermi interaction, suggesting that the strength of the weak interaction is the same for all fundamental particles, a cornerstone of the modern Standard Model. The impact of Sudarshan and Marshak's VF theory reverberated throughout the physics community. Their work provided a crucial stepping stone towards the development of the Standard Model of particle physics, the prevailing theory describing the fundamental forces and particles of nature. The VF theory is now recognized as a fundamental component of the Standard Model's electroweak sector, which unifies the electromagnetic and weak forces. It provides the foundation for understanding the interactions of quarks and leptons, the fundamental building blocks of matter, through the exchange of W and Z bosons, the carriers of the weak force. It is important to acknowledge the circumstances surrounding the independent discovery of the VF theory. Around the same time that Sudarshan and Marshak were developing their theory, Richard Feynman and Murray Gell-Mann independently arrived at the same formulation. This simultaneous discovery underscores the intellectual ferment of the era and the inevitability of certain breakthroughs given the convergence of experimental evidence and theoretical insights. While Feynman and Gell-Mann's work is also highly regarded, Sudarshan and Marshak's contribution is equally significant and deserves recognition for its pioneering role in shaping our understanding of weak interactions. There is no suggestion of impropriety on either side. The independent discovery highlights the intense scientific pursuit of the time. The modern relevance of the VF theory is undeniable. It remains a cornerstone of the Standard Model, taught in universities worldwide as a fundamental concept in particle physics. The theory's predictions have been extensively verified by numerous experiments, solidifying its place as one of the most successful theories in physics. While the Standard Model itself is believed to be incomplete, lacking explanations for phenomena like dark matter and dark energy, the VF theory continues to serve as a reliable and accurate description of weak interactions at energies accessible to current experiments. Future research in particle physics, exploring physics beyond the Standard Model, will undoubtedly build upon the foundation laid by Sudarshan and Marshak's groundbreaking work. Sudarshan's contributions to physics were not confined to the realm of weak interactions. He possessed a remarkable ability to challenge conventional wisdom and explore unconventional ideas, a trait that led him to investigate the possibility of particles traveling faster than light. The Standard Model, a cornerstone of particle physics, is taught in universities worldwide as a fundamental concept. The theory's predictions have been extensively verified by numerous experiments, solidifying its place as one of the most successful theories in physics. While the Standard Model itself is believed to be incomplete, lacking explanations for phenomena like dark matter and dark energy. The VF theory continues to serve as a reliable and accurate description of weak interactions at energies accessible to current experiments. Future research in particle physics, exploring physics beyond the standard model, will undoubtedly build upon the foundation laid by Sudarshan and Marshak's groundbreaking work. Sudarshan possessed an intellectual curiosity that extended beyond established paradigms. This led him to consider theoretical possibilities that challenged the very foundations of relativistic physics, specifically the concept of particles exceeding the speed of light. Prior to Sudarshan's investigations, the speed of light, denoted as c, was considered an absolute barrier in the universe. Einstein's theory of special relativity, published in 1905, established that the speed of light in a vacuum is constant for all observers, regardless of their relative motion or the motion of the light source. This postulate had profound consequences, including the famous mass-energy equivalence E equals mc squared and the relativistic effects of time dilation and length contraction. One implication of special relativity was the seemingly insurmountable difficulty of accelerating a massive particle to the speed of light. As the particle approaches c, its mass increases asymptotically, requiring an infinite amount of energy to reach the light barrier. Classical physics appeared to forbid any object from surpassing this cosmic speed limit. However, Sudarshan, alongside other physicists, questioned whether relativity unequivocally prohibited the existence of particles that always travel faster than light, rather than accelerating to that speed. These hypothetical particles were dubbed tachyons, derived from the Greek word tachys, meaning swift. The crucial distinction lay in the initial condition: could there be particles created with superluminal velocities from the outset, bypassing the need to accelerate through the light barrier? Sudarshan's exploration of tachyons involved a deep dive into the mathematical structure of special relativity. The challenge was to modify or reinterpret the relativistic equations in a way that could accommodate particles with space-like form momentum, a characteristic of fast-to-the-light objects. This meant grappling with concepts like imaginary mass and the implications for causality. A key question was whether the existence of tachyons would necessarily lead to violations of causality, potentially allowing for effects to precede their causes. One of Sudarshan's significant contributions was to develop a theoretical framework for describing the properties and interactions of tachyons. This involved extending the concepts of Lorentz invariance, a cornerstone of special relativity, to the realm of superluminal particles. Lorentz invariance dictates that the laws of physics remain the same in all inertial frames of reference. Sudarshan sought to determine how this principle could be adapted to describe the behavior of tachyons, even though their existence would seemingly challenge our intuitive understanding of space and time. Sudarshan co-authored several influential papers on tachyons, exploring their theoretical properties and potential interactions with ordinary matter. These publications delved into the mathematical formalism required to describe tachyons, including modifications to the standard relativistic equations of motion. For instance, a tachyon's energy, according to the relativistic energy-momentum relation, would become imaginary for real momentum, implying that tachyons might possess unusual properties compared to ordinary particles. One crucial aspect of Sudarshan's work was addressing the potential paradoxes associated with tachyons, particularly those related to causality. If tachyons could transmit information faster than light, it seemed to open the door to scenarios where one could send signals into the past, potentially altering events and creating logical inconsistencies. Sudarshan explored various ways to reconcile the existence of tachyons with the principle of causality, such as the reinterpretation principle, which suggested that a tachyon emitted forward in time by one observer might be interpreted as a tachyon emitted backward in time by another observer. This reinterpretation could potentially preserve causality by ensuring that no observer ever receives a signal from their own future. While Sudarshan's work on tachyons was primarily theoretical, it had a significant impact on the field of physics. It broadened the scope of theoretical investigations into exotic particles and alternative space-time geometries. Even though tachyons have never been experimentally confirmed, the theoretical exploration of faster-than-light particles pushed the boundaries of our understanding of the limits of physics. It prompted physicists to carefully examine the assumptions underlying special relativity and to consider alternative theoretical frameworks that might accommodate superluminal phenomena. Sudarshan's work on tachyons was influenced by the deep understanding of Lorentz invariance and the principles of special relativity he gained during his career. He was particularly inspired by the mathematical elegance and consistency of Einstein's theory, even as he sought to extend its boundaries. His exploration of tachyons can be seen as a natural extension of his earlier work on quantum field theory and particle physics, where he had already demonstrated a willingness to challenge conventional assumptions and explore new theoretical possibilities. His investigation into tachyons influenced later theoretical work by other physicists. While direct experimental evidence for tachyons remains elusive, the theoretical framework developed by Sudarshan and his colleagues provided a foundation for subsequent investigations into exotic particles and alternative spacetime geometries. It encouraged physicists to consider the possibility that our current understanding of the universe may be incomplete and that there may be phenomena beyond our current detection capabilities. The theoretical tools and concepts developed in the context of tachyon research have found applications in other areas of physics, such as the study of quantum entanglement and the foundations of quantum mechanics. Even without experimental confirmation, Sudarshan's theoretical exploration of tachyons remained a valuable contribution to the ongoing quest to understand the fundamental nature of space, time, and matter. Sudarshan also grappled with the perplexing implications of the Quantum Zeno Effect, a phenomenon where frequent measurements on a quantum system can effectively freeze its evolution. This counterintuitive result arises from the projection postulate of quantum mechanics, which posits that a measurement collapses the wave function of a system into a specific eigenstate. Repeatedly measuring the system forces it to remain in its initial state, inhibiting its natural tendency to evolve. The Quantum Zeno Effect presented a challenge to the prevailing understanding of quantum dynamics. It seemed to suggest that continuous observation could halt all change, a notion that clashed with the inherent dynamism of the quantum world. Sudarshan, with his characteristic insight, sought to clarify the theoretical underpinnings of this effect and resolve the paradoxes associated with continuous observation. His work delved into the mathematical formalism of quantum measurement, exploring the conditions under which the Zeno effect manifests and its limitations. He examined the role of the measurement apparatus and its interaction with the quantum system, demonstrating that the Zeno effect is contingent upon the specific details of the measurement process. Sudarshan's investigations revealed that the quantum Zeno effect is not an absolute barrier to quantum evolution, but rather a suppression of it. The degree of suppression depends on the frequency and strength of the measurements. Infinitely frequent measurements would, in principle, completely freeze the system, but any realistic measurement process involves a finite interaction time and a finite degree of disturbance. These limitations allow for some residual evolution, even under frequent observation. His contributions extended the Zeno effect to the realm of open quantum systems that interact with their surrounding environment. He demonstrated that the environment itself can induce Zeno-like behavior, effectively monitoring the system and inhibiting its evolution. This environmental monitoring arises from the constant exchange of energy and information between the system and its surroundings. The environment acts as a bath of fluctuating fields and particles, continuously probing the system and collapsing its wave function. The influence of the environment on quantum systems is a pervasive phenomenon, particularly relevant in the context of quantum computing and quantum information processing. Quantum computers, which rely on the delicate superposition and entanglement of quantum states, are highly susceptible to environmental noise. This noise can decohere the quantum states, destroying the quantum information encoded within them. Understanding and mitigating the effects of environmental decoherence is a major challenge in the development of practical quantum computers. Sudarshan's work on open quantum systems provided valuable insights into the mechanisms of decoherence and the strategies for combating it. He explored the use of quantum error correction techniques, which involve encoding quantum information in a redundant manner, allowing for the detection and correction of errors caused by environmental noise. He also investigated the possibility of engineering the environment to minimize its disruptive effects, creating a more stable and coherent quantum system. A key tool in the study of open quantum systems is the Lindblad equation, a master equation that describes the time evolution of the density matrix of a system interacting with its environment. The Lindblad equation incorporates the effects of both coherent evolution, governed by the system's Hamiltonian and dissipative processes, arising from the system's interaction with the environment. Sudarshan made significant contributions to the understanding and application of the Lindblad equation, developing techniques for solving it and extracting meaningful physical information. His work on the Lindblad equation and open quantum systems influenced later researchers in quantum control and quantum error correction. These researchers built upon Sudarshan's theoretical framework to develop new methods for manipulating and protecting quantum information. They explored the use of feedback control techniques, where measurements of the system are used to actively correct for errors caused by environmental noise. They also investigated the design of robust quantum gates, which are less susceptible to decoherence. Alan Turing's groundbreaking work on computability and the theoretical limits of computation served as a significant influence on Sudarshan's thinking about quantum mechanics. Turing's concept of a universal Turing machine, a theoretical device capable of simulating any computation, provided a powerful framework for understanding the nature of information and its processing. Sudarshan recognized the deep connections between Turing's ideas and the foundations of quantum mechanics, particularly in the context of quantum computation and quantum information theory. Sudarshan's publications on the quantum Zeno effect and open quantum systems offer concrete examples of his contributions to these fields. His papers, often co-authored with his students and collaborators, present rigorous mathematical analyses of the Zeno effect, exploring its dependence on measurement parameters and its implications for quantum control. These publications also delve into the intricacies of open quantum systems, examining the effects of various types of environments on quantum coherence and entanglement. They provide detailed derivations of the Lindblad equation and its applications to specific physical systems, such as atoms interacting with electromagnetic fields. The quantum Zeno effect continues to be a topic of active research in quantum optics and quantum information science. It has found applications in quantum computing, where it can be used to protect delicate quantum states from decoherence. It also plays a role in quantum control, where it can be used to manipulate the evolution of quantum systems with high precision. The principles underlying the quantum Zeno effect are also relevant to the development of new quantum technologies, such as quantum sensors and quantum metrology devices. Sudarshan's work on open quantum systems remains a crucial area of research in quantum information science. Environmental decoherence is a major obstacle to the realization of practical quantum computers, and understanding its mechanisms is essential for developing effective strategies for mitigating its effects. Researchers continue to explore new methods for quantum error correction, robust quantum control, and the design of decoherence-resistant quantum systems. The Lindblad equation, which Sudarshan helped to elucidate, remains a central tool in this ongoing quest to harness the power of quantum mechanics for computation and communication. The search for fundamental descriptions of quantum phenomena, which animated Sudarshan's work on open systems, also defined his most celebrated and contentious contribution to the quantum theory of optical coherence. This endeavor brought him to the very heart of a conceptual revolution, one that would redefine our understanding of light itself. The problem at hand in the early 1960s was profound. The invention of the laser in 1960 had produced a form of light with unprecedented properties, a pure, coherent beam whose behavior eluded description by the classical electromagnetic theory of Maxwell or the early quantum ideas of Planck and Einstein, which treated light as discrete photons. A full quantum mechanical framework was needed to characterize the statistical properties of this new kind of light. In 1963, Sudarshan published a paper that provided precisely such a framework. He formulated what is now known as the Sudarshan-Glauber representation, or, sometimes, with historical precision, the Sudarshan diagonal representation. His solution was to represent the density operator of any state of the electromagnetic field as a weighted average over coherent states. These coherent states, developed by Erwin Schrödinger and later championed by Roy Glauber, were the quantum states that most closely resembled a classical light wave. Sudarshan's insight was that any light field, classical or quantum, could be expressed as a superposition of these coherent states. The genius of his representation lay in its completeness. The weighting function he introduced, a quasi-probability distribution, could fully characterize any state of light. This completeness, however, came with a feature that many physicists of the era found deeply unsettling. For purely quantum states of light, like squeezed states or single photon states. Sudarshan's weighting function could take on negative values. This was a radical departure from classical probability theory, where probabilities are, by definition, always positive. For some, this made the representation seem formal, perhaps even unphysical. Yet, this very feature was a key to its power. It was a mathematical signature of the system's inherently quantum nature, distinguishing it from any possible classical description. Sudarshan had provided a universal tool for quantum optics. Around the same period, the Harvard physicist Roy Glauber was developing his own powerful formalism for quantum coherence. Glauber's work, which also utilized coherent states, led to what he called the p-representation for a large class of light fields, particularly those with classical analogs. Glauber's p-representation was mathematically identical to Sudarshan's diagonal representation. Glauber's extensive development of the theory of correlation functions and photon counting statistics provided a robust and accessible toolkit that was rapidly adopted by the community. The convergence of these ideas culminated in one of modern physics' most enduring academic disputes. In 2005, the Nobel Prize in Physics was awarded, with one half going to Roy Glauber for his contribution to the quantum theory of optical coherence. Sudarshan's name was absent from the citation. The omission triggered an immediate and vocal response from a significant portion of the theoretical physics community. Numerous physicists, including several Nobel laureates, wrote letters to the Swedish Academy, arguing that Sudarshan was the originator of the crucial diagonal representation. They pointed to the publication dates, with Sudarshan's paper appearing first. They argued that his formulation was more general, as it encompassed all possible quantum states from the outset, including the highly non-classical ones whose negative weighting functions were their defining characteristic. The argument rested on the very definition of discovery. Sudarshan had published the complete, universal mathematical key. His supporters viewed Glauber's subsequent work as a vital and brilliant elaboration, yet an elaboration on a foundation Sudarshan had already laid. The counter perspective often highlighted that Glauber's work created a more comprehensive and physically intuitive framework that made the theory truly useful and widely understood. The debate touches upon a subtle but recurring theme in the history of science: the distinction between the initial, perhaps abstract, conceptual breakthrough and the subsequent development that renders the breakthrough accessible and broadly applicable. The physics community continues to refer to the formalism as the Sudarshan-Glauber representation, a linguistic acknowledgement of a shared intellectual parentage that the Nobel Committee chose to divide. For Sudarshan, it was a profound disappointment, a public withholding of credit for what he and many of his peers considered his most important single contribution to physics. Across the disparate fields of particle physics, quantum optics, and foundational quantum mechanics, in Chandy George, Sudarshan's career forms a coherent intellectual arc defined by persistent interrogation of established axioms. His life's work was a testament to the power of theoretical physics to see beyond the visible and to construct new ways of thinking about reality. The common thread weaving through his contributions is a courageous willingness to pursue ideas to their logical conclusions, even when those conclusions led to uncomfortable or counterintuitive territories. His formulation of the V- theory of the weak nuclear force, conceived with Robert Marshak, exemplifies this spirit. It required looking past prevailing experimental data and trusting in the elegance and symmetry of a pure mathematical structure. The theory's ultimate vindication established a cornerstone of the standard model of particle physics, forever changing our understanding of the fundamental forces. His explorations of tachyons, particles theorized to travel faster than light, demonstrated a similar intellectual fearlessness. While tachyons remained hypothetical, Sudarshan's rigorous analysis showed that their existence could be compatible with the principles of special relativity, forcing physicists to refine their understanding of causality and locality. He treated the idea with the seriousness it deserved as a logical possibility within a cherished theory. In quantum optics, his diagonal representation for coherent states provided the essential language for the new field, a language capable of describing the full spectrum of light from the classical to the deeply quantum. This work, too, required a conceptual leap, embracing the idea of negative quasi-probabilities as a necessary feature of a complete quantum theory. Likewise, his work on the Quantum Zeno Effect and open quantum systems revealed a deep engagement with the subtleties of quantum measurement and the interaction between a system and its environment. He explored the very boundary between the quantum and classical worlds, providing tools like the Lindblad equation that remain indispensable for the development of quantum computing and information theory. Sudarshan's legacy, however, extends far beyond his bibliography of influential papers. He was a profoundly dedicated educator and mentor. As a professor for many decades, primarily at the University of Texas at Austin, he shaped the minds of generations of physicists. His lectures were renowned for their depth and clarity, and he possessed a rare ability to convey the intricate beauty of theoretical physics with passion and precision. He guided his students with a philosophy that encouraged independent thought and the courage to question orthodoxy, the very principles that animated his own research. His influence is therefore twofold. It resides in the equations and theories that bear his name, and it lives on in the intellectual DNA of the many scientists he trained and inspired. He was a physicist's physicist, more concerned with the internal consistency and logical beauty of a theory than with its immediate experimental confirmation or popular acclaim. His career demonstrates that the path of scientific progress is often complex, with contributions coming from many directions, and that the history of ideas is rarely a simple, linear narrative. E.C.G. Sudarshan stands as a figure of immense intellectual integrity, a theorist who consistently pushed the boundaries of knowledge. His life's work serves as an enduring reminder that the deepest insights into the nature of the universe often emerge from a willingness to challenge what we think we know and to follow the elegant, demanding logic of mathematics wherever it may lead.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.